America invented the airplane. America put the first human being on the moon. America built the jets that connected the world, wrote the rules that governed the sky, and ran the routes that made global travel possible. For the entire 20th century, if you wanted to understand where aviation was going, you looked at America. The answer was always there. That is no longer where you look. Right now, in cities across China, ordinary people with no pilot license, no flight training, and no aviation experience are climbing into two-seat aircraft, tapping a destination on a touchscreen, and flying there. Not in a test facility, not in a controlled demonstration. In real cities, on real routes, carrying real passengers who bought real tickets. Right now, a flying vehicle that folds out of the back of an electric truck is sitting on a waiting list with nearly 5,000 confirmed pre-orders at a price under $280,000. A comparable helicopter costs more than that and requires a licensed pilot, a dedicated landing pad, and between $100 and $300 per hour to operate. Right now, a personal flying vehicle is on sale in China for $4,937, less than most Americans spend on a secondhand car, less than some people spend on a holiday. A personal flying vehicle for the price of a used iPhone, and it actually flies. And right now, an engine built by a Chinese company for a family sedan that costs less than $10,000 has been certified by Guinness World Records as the most fuel-efficient, mass-produced engine ever built. 106 miles per gallon. In a car a regular family can actually buy, verified, stamped, official. These are not predictions. These are not concept renders sitting behind glass at a technology exhibition. These are things that exist today in the physical world, doing real things for real people. The biggest transformation in transportation since the invention of the automobile is not coming. It is already here, and the country leading it is not the one that led the last century of transportation innovation. This is the full story: where it started, how it happened, what has actually been built, why the West fell behind, what the obstacles still are, and what the next 10 years of getting from one place to another are actually going to look like. By the time we finish, the way you think about transportation will not be the same as when you started watching. Hit the like button right now before we go any further. This kind of deep research takes significant time, and every like directly helps this reach more people who need to see the full picture. Subscribe and turn on the notification bell. This story is moving fast, and you want to be there when the next chapter breaks. Let us go. America has been promising flying cars since 1917. That is not a typo. 109 years of promises. 109 years of concept art, investor presentations, magazine covers, and headlines that never turned into something you could actually buy. The flying car has been the most persistently promised and most consistently undelivered technology in the history of transportation. The first serious prototype flew in 1946. A man named Waldo Waterman built a three-wheeled aircraft that could take off from a runway and drive on a road. Magazines called it the future of personal travel. The future never shipped. In 2006, a group of MIT graduates founded a company called Terrafugia with serious backing, serious engineering talent, and a serious attempt to turn the flying car concept into a product people could buy. They spent over a decade trying. They never sold a single unit to a single customer. In 2017, the company was quietly acquired by a Chinese firm. Most Americans never noticed. In 2024, Lilium, a German electric vertical takeoff and landing startup that had raised over $1 billion, roughly the annual economic output of a small Pacific Island nation, filed for bankruptcy. Archer Aviation is still waiting for FAA certification. Joby Aviation is still waiting. Wisk Aero is still waiting. The Western flying vehicle industry did not fail quietly. It failed loudly, expensively, and repeatedly, leaving behind a trail of spent capital, talented engineers, and engineering lessons learned the brutal way. But here's the detail that changes everything. Every one of those failures left something behind: data, patents, aerodynamic research, battery chemistry insights earned through real testing rather than theoretical modeling, engineering talent that scattered across the industry and kept working. Each collapsed Western startup was, without meaning to be, a research document that anyone paying close enough attention could read and learn from. China was paying close attention. And here is where the common story about China gets this wrong. The assumption, stated or unstated in most Western coverage, is that China copies, that it waits for the West to do the hard work of genuine innovation and then manufactures the result cheaper and faster. In some industries, in some eras, that story had truth to it. In flying vehicle technology, the story is exactly backwards. China did not copy Western flying cars. China watched Western flying cars fail and built something different. When Lilium's jet-powered design hit aerodynamic complications and funding walls, Chinese engineers had already moved towards simpler multi-rotor designs that were cheaper to build, cheaper to certify, and more reliable in real-world conditions. When Western startups burned through capital chasing single-pilot certified aircraft that required expensive licensed operators, China built fully autonomous systems that removed the human from the equation entirely, eliminating the licensing requirement and the human error risk simultaneously. When American companies spent years in negotiation with the FAA over certification frameworks that did not yet exist for this category of vehicle, China's Civil Aviation Administration was actively building those frameworks in parallel with the aircraft they were designed to certify. Two builders working on adjacent properties. The Western builder starts with the most ambitious blueprint imaginable, a structure with custom everything, and watches the foundation crack under the complexity. The Chinese builder studies what went wrong, builds something that passes inspection on the first attempt, and is already renting out every unit while the Western builder is still on the second floor. By 2023, China had more than 30 active electric vertical takeoff and landing companies funded and scaling simultaneously. 30, not 30 companies competing for the same slice of a fixed market. 30 companies generating 30 parallel streams of engineering progress, feeding lessons into a shared ecosystem that got cheaper and smarter with every passing quarter. No single Western company could compete with that. No collection of Western companies working separately inside separate regulatory environments and separate funding structures could compete with it either. The floor underneath China's flying vehicle industry was built deliberately, over years, with government commitment treating low-altitude aviation, everything flying below 3,000 feet, as a national economic priority. The infrastructure, the regulation, the manufacturing scale, the supply chain, all of it constructed in parallel so that when the aircraft were ready, everything needed to support them was already there. That floor is now producing things that are genuinely difficult to process if you are accustomed to thinking of flying vehicles as a technology that is always 5 years away. Let us go through what actually exists, not what is planned, not what is in development, what you can buy, ride, or watch flying right now. The vehicle that started the public conversation is called the EHang EH216S. It seats 2 passengers, it has 16 independent rotors across 8 folding arms, it flies itself entirely. When you climb inside, you will notice something immediately. There is no joystick, there are no controls, there is no instrument panel. The cabin looks less like a cockpit and more like a very small passenger pod because that is exactly what it is. You are not the pilot. You were never going to be the pilot. You tap a screen, select a destination from a set of approved routes, and a ground-based AI control center manages everything from that moment until the skids touch down at the other end. Altitude, navigation, speed, obstacle avoidance, landing approach, all of it handled by the system. There is no override, no emergency joystick, no manual control you can reach for if something feels wrong mid-flight. For the full duration of the journey, you are a passenger in the most literal sense of the word. Most people, when they hear that, take a small step backward. The detail that changes the entire conversation is in the certification record. In October 2023, the EHang EH216S became the first electric vertical takeoff and landing aircraft in history to receive full type certification from China's Civil Aviation Administration. Not a test permit, not a research exemption, a full commercial certification, the same category of approval a commercial airliner has to earn before it carries a single paying passenger. Government inspectors examined every part of the design, tested it under demanding conditions, and officially confirmed it was safe for commercial passenger operation. From that moment, it went to work. Tourism flights in Guangzhou, short-range transit routes in Hefei, real passengers, real tickets, real flights happening right now while you read this. Over 300 units have already been sold, not pre-ordered, delivered. Certified flying vehicles in active commercial operation, accumulating real flight hours and feeding real engineering improvements back to the development team in real time. And the passengers climbing into these pods are not nervous test volunteers or company employees logging mandatory hours. They are ordinary people, tourists, commuters, curious travelers who looked at an autonomous flying pod with zero controls and said yes. They climbed in, flew, landed, and did it again. That single fact tells you more about where this technology actually stands than any specification sheet. The trust is already there. The public has already decided. The question the industry spent a decade asking, whether people would actually use autonomous flying vehicles in the real world, has been answered in the most definitive way possible. By people using them, the EHang is not the only vehicle worth understanding. The Xpeng Land aircraft carrier approaches the flying vehicle problem from a completely different angle. Rather than building one machine that tries to do everything, Xpeng engineered two machines optimized for their specific environments that work together seamlessly. A full-size electric vehicle that drives on normal roads, and a flying module with 6 propellers that sits on top during transit, detaches when you are ready to fly, lifts off vertically, completes the flight, then folds back down and reattaches to the ground vehicle when the flight is done. The entire transition from flight mode to road ready takes 5 minutes, demonstrated publicly, on film, repeatedly. The ground module delivers approximately 500 miles of driving range. The price sits under $280,000, which undercuts a comparable helicopter purchase before you factor in the licensing, the dedicated landing infrastructure, and the $100 to $300 per flight hour operating cost that comes with it. Nearly 5,000 people have placed confirmed pre-orders with real deposits. For context, 5,000 units is roughly the entire annual global production volume of Lamborghini across every model and every market for a full year. The factory in Guangzhou already exists with an annual production capacity of 10,000 units. 10,000 flying vehicles per year is more than the entire Western world has ever certified in its entire history of attempting to build them. The Autoflight Prosperity set the world record for the longest flight ever completed by an electric vertical takeoff and landing aircraft of its kind, covering 155 miles on a single charge. 155 miles fully electric. The distance from Washington, D.C. to New York City without burning a single drop of fuel. It functions as an air taxi, flying passengers autonomously between city destinations, with a safety architecture that includes multiple independent protection layers and an AI capable of deploying a ballistic parachute within a fraction of a second if a critical component fails mid-flight. The XTI Trifon 600 operates at the far end of the ambition scale. It uses 3 ducted fans, 2 of them sitting inside the wings and capable of rotating 90 degrees. At takeoff, they point straight up, lifting the aircraft vertically. Once airborne, they rotate forward and the aircraft transitions into high-speed horizontal flight. It carries 6 passengers at 380 miles per hour, reaches 30,000 feet, and covers nearly 1,500 miles without requiring an airport, a runway, or a terminal. It takes off from a corporate parking lot, a rooftop helipad, or a private property. A journey that currently takes 5 to 6 hours on congested highways becomes a 90-minute door-to-door flight. The Jetson 1 weighs 190 pounds, less than most motorcycles, runs on 8 electric motors, hits 63 miles per hour, and in many jurisdictions requires no pilot license to operate. The onboard flight computer handles stabilization automatically. If you release the joystick mid-flight, the aircraft hovers and waits. The company's explicit goal was to make personal flight feel as natural as driving a car, and early owners consistently described the experience in those terms. The Airspeeder Mark III was built for the world's first flying vehicle racing series. Pilots in remote locations wearing virtual reality headsets race these aircraft through 3-dimensional aerial courses at speeds up to 186 miles per hour. The collision avoidance software, sensor arrays, lightweight materials, and battery management systems developed under those racing conditions are being pushed to absolute limits in real competition. Every close call, every record lap, every mechanical failure generates engineering insight that makes the next generation of civilian aircraft safer and more capable. Every major racing competition in history has served this function. NASCAR gave us tire science and engine reliability under sustained stress. Formula One gave us carbon fiber and advanced aerodynamics. Those technologies found their way into the cars regular people drive to work. The Airspeeder series is doing the same thing for flying vehicles in real time. And in February 2026, a Chinese company called Autoflight unveiled something that forced the entire industry to recalibrate what the words flying vehicle even mean. They called it the Matrix. 5 tons of aircraft, a wingspan of 66 feet, wider than 3 standard American highway lanes placed side by side. 10 passengers, fully electric, the largest electric vertical takeoff and landing aircraft ever built. Not a concept, not a rendering, a physical aircraft that exists in the world, built by the same ecosystem that put a personal flying vehicle on sale for under $5,000 in the same calendar year. That personal flying vehicle deserves its own moment, $4,937. The price that generated thousands of videos, international headlines, and a reaction from Western journalists that ranged from astonishment to outright disbelief. The vehicle is not a car with wings. It is a single-seat electric aircraft that functions like an enlarged personal drone. Compactness, simplicity of design, and manufacturing scale rather than expensive custom components kept the price at a level that seemed impossible to the Western aerospace industry, accustomed to calculating certification costs alone in the millions. The honest version of that price requires some nuance. The base figure covers the body, motors, and core electronics. Batteries with extended range cost additional. An autopilot system costs additional. Certification for urban flight operation adds registration, insurance, and in some jurisdictions, training requirements. The total landed cost is higher than the headline figure, but even with all of those additions factored in, the final number remains several times lower than anything the Western flying vehicle market has produced. China applied to this category the same approach it applied to electric vehicles, to consumer electronics, to battery manufacturing, mass production, aggressive cost optimization, ready-made technology from adjacent industries adapted rather than invented from scratch, government support reducing taxes and subsidizing key components. The result is a price point that was not supposed to be possible for another decade. It is possible now. The vehicles are flying, the orders are arriving. The question has shifted from whether this technology can reach consumers to what happens when it does at scale. Here is the answer to that question that nobody in the promotional materials talks about. The sky is not empty. It is one of the most tightly managed spaces on Earth. Every corridor, every altitude band, every approach path around every airport is governed by rules written for a world where flying was something airlines did, not something individuals did on a Tuesday morning to avoid traffic. Those rules were not designed with a $4,937 personal flying vehicle in mind. Rewriting them is not a weekend project. Think of it like the early days of the internet. The technology arrived before the legal framework did. For years, the technology sat waiting while governments, lawyers, and regulators tried to agree on what the rules should even look like. Flying vehicles are at exactly that moment. The product exists, the rule book is still being written. In the United States, the FAA governs everything that moves through American airspace, and it moves carefully, deliberately, and sometimes frustratingly slowly. The certification process for a new aircraft category can take years, sometimes a full decade. American electric vertical takeoff and landing companies like Joby and Archer have been navigating that process since the early 2020s and are still not carrying paying passengers on commercial routes today. They are doing serious engineering work under a serious regulatory framework, and the work is real. But the timeline reflects the genuine difficulty of what certification requires. China solved the regulatory problem differently. The Civil Aviation Administration of China did not wait for the aircraft to arrive before building the framework. It built the framework alongside the aircraft in parallel so that by the time the EHang EH216S was ready for certification, the rulebook it needed to pass already existed. That is not an accident or a coincidence. It is a deliberate policy decision made years in advance at the national level. The cities are the next layer of the problem. A modern city is not an open field. It is a labyrinth of power lines, communication antennas, high-rise buildings, bridges, and infrastructure obstacles that turn the airspace above an urban area into something considerably more complicated than the open sky above a rural testing ground. Without clearly defined air corridors, standardized routes, and traffic management systems capable of coordinating thousands of simultaneous flights. Mass urban flying vehicle deployment creates problems faster than it solves them. China is testing dedicated air corridors in multiple cities, zones where drone flights are managed separately from air vehicle routes. Radar systems, cameras, and automatic emergency landing protocols installed along established paths. The infrastructure is being built, but it is being built at a pace considerably behind the pace of vehicle development. Even in China, the most developed market for this technology, the infrastructure gap is real. In the United States, the situation is more complex. Building a network of landing infrastructure, charging stations, and air traffic management systems for personal flying vehicles requires investment, coordination across multiple levels of government, and years of approvals even before the first vehicle lifts off. The technology is ready in ways the infrastructure is not. Europe faces a different version of the same problem. Dense urban development, strict noise standards, and regulatory frameworks that require coordination across multiple national authorities before a vehicle can operate commercially across borders. A personal flying vehicle that works perfectly in Shanghai cannot be imported to Paris and flown legally without meeting an entirely different set of requirements developed by an entirely different regulatory system. There is also the charging infrastructure question. Flying vehicles run on batteries. Batteries need charging. Charging requires ground infrastructure that does not currently exist at the scale mass adoption requires. The electric vehicle industry spent years solving the analogous problem for cars, and the charging network still has significant gaps in most markets. The flying vehicle industry is starting from zero. The environmental question is one that the promotional materials consistently skip past, and that deserves honest attention. Electric motors and no exhaust emissions make flying vehicles look like an environmental improvement over conventional transportation at first glance. The reality is more complicated. Electricity has to be produced somewhere. In China, where a significant portion of electricity generation still comes from coal-fired power plants, the emissions reduction benefit of an electric flying vehicle is meaningfully reduced by the emissions produced generating the electricity that powers it. The calculation improves as the electricity grid decarbonizes, but it does not start from zero. Battery production requires lithium, cobalt, nickel, and rare earth elements. Extracting those materials from the ground is not a clean or simple process. It involves open pit mining operations, significant land disruption, and in the case of cobalt specifically, documented concerns about the conditions under which it is mined. These are not fringe concerns. They are documented ongoing issues that the battery industry is working to address but has not yet resolved. Battery disposal represents a challenge the industry has not fully solved at current electric vehicle scale, let alone at the scale that mass flying vehicle adoption would require. Thousands of spent aircraft batteries cycling out of service annually represents a material management challenge with real environmental implications that are not accounted for in the promotional framing. The noise issue is more immediate. Even the quietest electric vertical takeoff and landing vehicles produce significant sound during takeoff and landing phases. In urban environments where these vehicles would operate most frequently and overpopulated areas where the density of operations would be highest, the cumulative noise effect of high-volume flight operations represents a genuine quality of life issue that city planners and regulators are going to have to address before mass adoption becomes politically sustainable. None of this means the technology should not be developed or deployed. It means the honest version of the environmental story is considerably more complicated than electric equals clean. The military dimension of this story is one that Western governments are thinking about considerably more carefully than the public conversation reflects. Every technology that begins in civilian transportation eventually finds military application. The automobile gave armies mobility, aircraft gave armies air superiority, satellites gave armies global positioning and communications. The pattern is consistent, and the timeline between civilian deployment and military integration has shortened dramatically in recent decades. The Pentagon is actively investing in air mobility programs for ground forces. Compact autonomous aircraft capable of rapid troop movement, resupply delivery, and medical evacuation in environments where conventional vehicles cannot operate effectively and helicopter costs are prohibitive. The same capabilities that make a 4,000 $937 flying vehicle attractive for civilian logistics have obvious military applications for moving personnel and supplies in terrain that roads cannot cross. China's military engineering programs are developing autonomous cargo drones capable of supplying forward positions with ammunition and medical supplies, reconnaissance platforms that can operate in environments where larger aircraft present too large a target. The dual-use nature of flying vehicle technology is not a future concern. It is a present reality that both sides of this competition are managing actively. The concern that receives less public attention is the asymmetric threat dimension. A civilian flying vehicle platform that is cheap, widely available, and capable of carrying a payload through airspace that existing air defense systems were not designed to monitor at that altitude. And that flight profile represents a security challenge that defense planners in every major country are actively working to address. The same technology that lets a farmer inspect crops from the air or a logistics operator deliver medicine to a remote village can be misused in ways that require new detection and response capabilities. This is not an argument against the technology. It is an argument for the regulatory and security frameworks to develop at a pace that keeps up with the technology itself. On current evidence, the frameworks are running behind the technology in most markets. Now let us talk about the engine, because everything we have covered so far exists in the air. And while engineers were figuring out how to make the sky accessible to regular people, a different group of engineers was solving a problem that affects every single person who has ever stopped at a gas station. In April 2026 at the Beijing Auto Show, a Chinese company called Geely walked onto the stage and displayed a number on a giant screen that left automotive engineers across 3 continents genuinely silent: 106 miles per gallon. Not in a laboratory test under ideal controlled conditions. On a public road in Hainan province, in a mid-sized family sedan with Guinness World Records officials on site for the entire test, verifying and certifying every measurement taken. 106 miles per gallon. The highest fuel efficiency ever recorded for a mass-produced passenger vehicle. Official, verified, stamped. To understand why that number stopped the automotive world, you need to understand one thing about how engines work. When gasoline burns inside an engine, only a fraction of that energy actually moves the car forward. The rest escapes as heat through the exhaust pipe or gets absorbed into the engine components themselves. The percentage that actually becomes forward motion is what engineers call thermal efficiency. A regular gasoline engine in the car sitting in most driveways right now converts approximately 30 to 35% of its fuel into motion. Everything else is wasted heat. Toyota, the company that invented the modern hybrid and spent 30 years refining it, achieved 41% thermal efficiency in its most advanced engine. For years, that was the gold standard, the number every competitor aimed for and nobody matched. Geely's new engine, the BHE15, hits 48.41%, certified by Guinness, verified by independent observers, stamped in the record books as the highest thermal efficiency ever achieved by a mass-produced engine. Here is the comparison that makes that number viscerally real. The engines inside Formula One racing cars, the most sophisticated internal combustion engines ever built, the ones that cost millions of dollars each and are rebuilt after every single race, operate at around 50% thermal efficiency. Geely built an engine for a family sedan priced under $10,000 that sits within touching distance of Formula One performance. That sentence should not be possible. The record books say it is. When that engine is paired with a 308 horsepower electric motor and an AI energy management system that continuously decides in real time whether to use the engine, the battery, or both, the result is 106 miles per gallon on a public road in a car a regular family can actually buy. Toyota drove a Prius from Los Angeles to New York City in 2024 to showcase peak hybrid efficiency. That celebrated journey averaged 92.9 miles per gallon, and the automotive media treated it as a landmark achievement. Geely's system beats it by more than 12% in a vehicle that costs a fraction of the price. And Geely is not doing this alone. BYD, the company that recently surpassed Tesla to become the world's largest electric vehicle manufacturer, launched its 5th-generation hybrid system with 46.06% thermal efficiency. Their top model travels over 1,300 miles on a single tank, combined with a full battery charge. the driving distance from Miami to Boston without a single fuel stop. Other major Chinese manufacturers, including Chang'an, Seres, GAC, Chery, and Great Wall, have all launched similar ultra-efficient powertrains within the last 18 months. A thermal efficiency number that was cutting-edge laboratory performance just a few years ago is becoming a baseline expectation across the Chinese market. Meanwhile, conventional engines produced in Detroit by Ford, General Motors, and Stellantis are still operating between 30 and 35% thermal efficiency. That gap does not close quickly. Redesigning an engine platform, retooling a factory, retraining engineers, and getting a new product through certification and into production takes years. The distance between where the most efficient engines are and where conventional combustion engines are is growing, and it is growing fast. What makes this reach beyond Chinese borders is the ownership structure behind it. Geely does not only sell cars under its own name, it owns Volvo, it owns Polestar. It runs a major luxury joint venture with Mercedes-Benz. It actively licenses its powertrain technology to other manufacturers through its Horse Powertrain Alliance. These ultra-efficient engines will appear inside European and American vehicles within the next few years, whether traditional legacy brands develop their own versions or not. The record that was set in Hainan province is coming to a dealership near you, regardless of where you live. Step back now and look at everything as a single picture. Flying vehicles are already real, already certified, already carrying paying passengers on commercial routes. Some of them remove the need for a pilot entirely. Some fold out of the back of a truck and deploy at the press of a button. Some take off from a parking lot and land in another city. The sky is becoming genuinely accessible to regular people in a way that was not possible even 5 years ago. At the same time, the engine powering ground transportation just hit a level of efficiency that was previously accessible only through multi-million-dollar Formula One budgets in a vehicle that costs less than a decent second-hand car. These are not two separate stories. They are part of the same transformation. The walls between what counts as advanced technology and what regular people can actually access and afford are coming down faster than most people realize. Think about what happened with smartphones. In 2000, a mobile phone made calls. By 2007, it had replaced your camera, your map, your music player, and your internet connection. By 2012, it was replacing your wallet and your boarding pass. Industries that had existed for decades could not keep up with the pace of change. Photography, navigation, music, retail, physical media, all of them transformed in the space of a few years by a device that fit in a pocket. Transportation is doing the same thing right now. Electric motors, autonomous flight systems, AI energy management, ultra-efficient hybrid powertrains, and rapidly falling production costs are combining into something that will do to cars and planes what the smartphone did to cameras and maps. The obstacles are real, regulatory frameworks are still being written, infrastructure does not yet exist at the scale adoption requires. Environmental calculations are more complicated than the promotional materials acknowledge. Security frameworks need to develop at the pace of the technology. And the public trust required for autonomous flying vehicles to become genuinely mainstream will need to be built one flight, one passenger, one uneventful landing at a time. But the technology is not waiting for the frameworks. It is already in the air, already in the record books, already in the hands of the people who build things rather than the people who draw blueprints. America owned the sky in the 20th century. It built the jets, wrote the rules, and ran the routes. It invented the airplane, funded the research, trained the engineers, and turned commercial aviation into the infrastructure that connected the modern world. The 21st century sky is being claimed right now, not with fighter jets and moon rockets, with a foldable 6-propeller vehicle that deploys from a truck bed in 5 minutes, with a 2-seat autonomous pod that carries tourists over a Chinese city while they sit with nothing in front of them but a touchscreen and a view, with an engine for a family sedan that sits within 2 percentage points of Formula One performance and gets certified by Guinness World Records on a public road. China did not copy its way to this moment. It watched a century of Western promises fail, learned from every failure, built the floor that the West never built underneath its own talent, and produced things that are genuinely difficult to explain away as temporary or marginal. The $4,937 flying vehicle is not the beginning of a product launch. It is the beginning of something considerably larger. The same transformation that gave China the road, the rail, and increasingly the sea, arriving now in the sky. The only question that matters from this point forward is not whether this transformation is happening. It is whether the rest of the world is watching closely enough to understand what is required to participate in it rather than simply observe it from the ground. That answer is still being written. And unlike the last 100 years of flying car promises, the writing is happening very fast. If this gave you a complete picture of something you were only seeing in pieces before, hit the like button. It genuinely helps this reach more people who want the full story rather than the headline version. Subscribe and turn on notifications. The next chapter of this story is already in motion. Drop a comment and tell me honestly. Between a flying vehicle that lifts off from your driveway and an engine that carries you over 1,000 miles on a single tank, which one changes your daily life first? I read every single one. See you in the next one.